Okay, before we dive into three dimensions, let's see what we've been talking about, what it looks like algebraically, which will be more comfortable for some people uh, dealing with algebraic vectors than we did with all this stuff on the plane, like geometric vectors. What does this mean for algebraic vectors? So we want to show that this vector x, which is 4, -19, a vector on our xy plane, can be written as a linear combination of these two vectors. Remember that x is just 4i minus 19j, but we want to show that, well, this is a spanning set and it works as well. So let's do that. I've got all this stuff written. I'm just going to go through it try and go through it very quickly. You can pause and write as you see fit. All right, so we want to show that, I'm missing a letter there, so let me write that letter in there. There should be a B in there. Um, we want to show that x is a linear combination of our basis vectors, our spanning set u and v. Well, okay, well that means we've got x is equal to a times u plus b times v. And that gives me, when I do some algebra, scalar multiple, and then combine those two, 2a plus b is that the x coordinate, and then negative 3a plus 5b is the y coordinate. And if these two vectors are equal, then their x coordinates have to be equal and their y coordinates have to be equal. And I want to show you that. That's this right here. There's the x coordinates. This is the y coordinates. Now, what do I have? I've got two equations, two unknowns, grade 10 style. And so how do I solve those? I could use substitution, like move the 2a over to this side and put in this. I'm using elimination just for funsies, for no particular reason besides it just occurred to me to do it that way. So I multiplied this one by 5, the first equation by 5, and I got that. And then I multiplied this one by -1 so I could add. And again, the idea for elimination is we multiply so some of the coefficients of one of the variables would cancel. I could have multiplied this one by 3 and this one by 2, but I saw that I could multiply that one by 5, add, and I get 13a is equal to 39, a equals 3, substitute back, bing, 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 b equals -2. And so what does that mean? I can get this vector x by taking 3 copies of u and subtract 2 copies of b, and then I'm going to get x. And I can see that algebraically, and if you actually graph these vectors on a Cartesian grid, you'll see that that's true as well. Part B is maybe a little bit more fun. Show that any vector u with the coordinates x and y, I don't care what any vector can be written as a linear combination of these two spanning set vectors. By the way, this right here, that is our proof. We're proving that these two vectors are basis vectors or spanning set vectors. Remember, those two things mean the same thing. Okay, so here we go. Here comes the algebra. In fact, it's this exact same thing. We want to find these values of a and b. Remember, that's our idea. We want to have a equals 3 and b equals 2, except for it's not going to be that easy because we've got x and y are general coordinates. So we're actually going to have a formula for a in terms of x and y and a formula for b in terms of x and y, and we know we'll be done when we have a equals some formula and b equals some other formula. And in here are going to be x's and y's. That's the goal. Are you set? Okay, so same trick. Multiply by the scalars, compare coordinates, so I get the x coordinate is equal to 2a plus b. And I get the y coordinate is equal to -3a plus 5b. You see, I just distributed the a, collected up the 5b, and then I get 2 equations, 2 unknowns. And I'm going to pull the same trick. I'm going to try and eliminate the b's here. And I'm using elimination. You can use substitution. You can eliminate the a's first or the b's first. Doesn't matter. So I multiplied this one by 5, multiplied that one by -1, and then I'm adding down. and the b's disappear just like I was planning. On the left-hand side, I get a formula, and I knew I was going to get a formula for x and y. Divide by 13, and then I get my formula for a. To get my formula for b, I'm substituting back into equation 1 here. So I get 2 times a plus b. Solving for b gives me an awful formula, but it involves x's and y's. And then I get that. There's my formula for b. So now I know any old vector xy is a times the first vector and b times the second vector, and I get that expression. Notice that if I wanted to, and of course I want to, I could use 4, negative 19 here. 4, negative 19. I could put x is 4, y is negative 19, and see if I get the same values as I did for a. I'll do this for the a coordinate. This is going to be 20. 5 times 4 is 20, plus 19 over 13, that's 39 over 13. A is equal to 3, and look, yep, that worked for this one value, and it's going to work in general. Dandy. What's part C? Part C is to show that this other set of vectors is not a spanning set. All right, we just spent 2 questions figuring out how to show or use a spanning set, but now how do we show it's not? Well, this isn't the case then. We want to show that this is the case. We want to show that one of these things are true, and maybe this one here is the most mathy, and that's what I'm going to say. I'm going to say a linear combination of our potential basis vectors that we were given is equal to 0, and I'm going to find some values of a and b that are not 0. I'm going to do it this way first because we've done it that way before. Okay, this is part C. So there's my method 1. Here's my potential spanning set vectors, basis vectors, and I want to show that this is equal to 0 for some a and b, not both 0, because I know that's how I show it's not a spanning set. And I get a little equation that I end up with. Distribute the a, distribute the b. I get an x coordinate equal to 0 and a y coordinate equal to 0. 2 equations, 2 unknowns. Bing, bing, bing. Solve, solve, solve. And I get that case 0b equals 0. Essentially, when I use elimination, both sides are eliminated and the right sides are eliminated. So what does that mean? Any value that I pick for b is a solution. There's an infinite number of solutions. And I don't want to spoil my method 2 over here yet, so I'm going to reveal it this way. So for instance, an easy one to say that it's true is we could just swap the a and the b values. So make this 12 by letting a equal 4 and b equaling 3, and then that's going to make 0, right? So that one works. But I could have picked any value for a, solved this equation for b, and I get any value would be, pick any value k. Doesn't matter, some scalar k. And then I put that in and then solve for b, and I get b equals 3/4 k. And then that gives me my infinite number of solutions. So as long as k is not equal to 0, I've got a combination of a and b that give me a linear combination of my 2 spanning set vectors where a and b are not both 0 gives me the 0 vector. That shows not a spanning set. I'll say, okay, that's fine. Is there an easier way? Yes, there is, in fact. Remember, way back when, on this first slide, one of the things we said is, well, if they're parallel, obviously they're not a basis for space, because I can go linear combinations of vectors on a line or back and forth on the same line. I'm not going to get the entire plane. Well, okay, but how do I show that algebraically? Well, this I can show algebraically. I can show that they are scalar multiples algebraically. And that's the key, right here. Are they scalar multiples? And I end up with, yes. And in fact, U is negative 2/3 K. And perhaps you saw that early on, that if I took a minus 3 out of this one, I'd get 3, 2. And I take a 4 out of this one, I get 3, 2. These are scalar multiples of each other. And that's a quick way to show that they're parallel and that they're not a spanning set. They are not a spanning set. Okay, are you ready now? Are you ready to go into 3 dimensions? Not me, not yet. I'm going to pause this and make another short video in a moment.